Welcome back to the discussion, and in the last lecture we had seen that you can take the Fourier transform of a lattice of points whose density at any point is given by this expression. This is in 3 dimension, we had done it for 1 dimension, but this is the general case of a 3D lattice of points. And the requirement rho of r is the number density of points at any point r in the lattice. So, you have a lattice of points, a periodic structure, here I am showing it in 2 dimension, okay, and for any point r in this lattice, the number density at that point is given by rho of r, and the requirement of translation invariance, which is a very important aspect of a Bravais lattice, translational invariance, requires that if I go from this point r and I translate by an amount which is given by my lattice vector r bar, where this is r plus capital R, then the density at r plus capital R, namely at this point, should be exactly identical to the density at this point, and that is written out here. And this then satisfies the condition of a Bravais lattice, where this vector r is n1 a1 plus n2 a2 plus n3 a3. This is your translation vector r of the lattice. n1, n2, n3 are the indices or the components along a1, a2, a3, which are the fundamental translation vectors of the lattice. And this translation invariance, so then rho of r you can do a Fourier expansion, rho of r you can write it as summation over some vector g, rho g are the Fourier components e raised to I g bar dot r bar, where I am taking the Fourier expansion in terms of this vector g. And if I do translation invariance, then the requirement for translation invariance gives me this condition that e raised to I g bar dot r bar, r is your lattice translation vector, e raised to I g bar dot r bar should be equal to 1. And this suggests that g bar dot r bar is 2 pi m. So, for any lattice in real space given by r bar is equal to n1 a1 plus n2 a2 plus n3 a3, for any lattice which is in real space, your actual 3-dimensional space that we are living in, for any lattice in real space where you can generate the lattice using this translation vector r, corresponding to any such lattice, you can generate another lattice which is given by this vector g, where g bar dot r bar should be equal to 2 pi. And this vector g is corresponding to taking the Fourier transform of the real lattice. So, corresponding to any lattice in real space which is generated by using this condition, namely you have a set of points in real space. So, given a crystalline solid, you first make a Bravais lattice using this translation vector, where you can go from any point on the lattice to any other point using this sort of a translation vector. You will have to define your a1 and a2 appropriately, whatever is your choice that you want to do, and then using these you can generate your lattice points. But you can make another construction, and that second geometrical construction is with these vectors g, where these vectors g satisfy the condition that g bar dot r bar is equal to 1. Okay. Now, we write this vector in terms of, we have 3 components of this vector. We write it as h times g1 plus k times g2 plus L times G3, and R you already know is equal to N1A1 plus N2A2 plus N3A3. Now let us say, let A2 and A3 be equal to 0. Okay. Then what does this condition mean? G bar dot R bar is equal to 1 implies H times G1 plus K times G2 plus L times G3 dot N1 A1 is equal to 1. You just satisfy, put in this A2 equal to A3 and put it back here. This is your condition. For any arbitrary value of N1, this condition can be satisfied by considering G1 dot A1 should be equal to 2 pi, and so the condition that G bar dot R bar is equal to 2 pi, G2 dot A1 should be equal to 0 and G3 dot A1 is equal to 0. So the condition that G bar dot R bar is equal to 2 pi gives us our first condition that G1 dot A1 should be equal to 2 pi, G2 dot A1 should be equal to 0, G3 dot A1 should be equal to 0. Similarly, take A2 not equal to 0, A1 and A3 equal to 0, and you will get the condition that G2 dot A2 should be equal to 2 pi, G2 dot A1 should be equal to 0 and G3 dot and G1 dot A2 should be equal to 0 and G3 dot A2 should be equal to 0. So this says the above condition G1 dot A1 equal to 2 pi and G2 and G3 dot A1 is equal to 0 suggests that G2 and G3 are perpendicular to A1. So this directly gives us a way to construct G1, G2 and G3. Similarly, G2 is having some component along A2, but G1 and G3 are perpendicular to A2. Okay, and you can write down the same thing, G3 dot A3 is equal to 2 pi and G1 dot A3 should be equal to 0 and G2 dot A3 should be equal to 0. So the condition that G bar dot R bar, which is coming from the condition that G bar dot R bar is equal to 1, this gives us this condition, gives us a way to construct these vectors G1, G2 and G3. In general, I can rewrite all these conditions as Gi dot Aj is 2 pi delta Ij, where delta Ij is equal to 0 for I not equal to j. So you put I equal to 1 and j equal to 1, then G1 dot A1 is equal to 2 pi, I equal to 1 and j equal to 2 implies G1 dot A2 is equal to 0 and so on. So this is a condition that one uses to find out these vectors G1, G2 and G3. So corresponding to any real space lattice which is generated by the translation vector N1 A1 plus N2 A2 plus N3 A3, one can find another lattice where G bar dot R bar is equal to 2 pi, and this gives a condition, and this G is written as H times G1 plus K times G2 plus L. Using the above condition, if we know A1, A2, A3, one can construct G1, G2, G3 by using the condition Gi dot Aj is equal to 2 pi delta Ij. Now, how can we write? Is there a simple way to write this down? There is of course a simple way to write this down. G1 can be written as 2 pi A2 cross A3 divided by A1 dot A2 cross A3. One expression which actually satisfies this condition is writing G1 like this, and one can easily check G1 dot A1 is 2 pi A1 dot A2 cross A3 divided by A1 dot A2 cross A3. This is nothing else but 2 pi, and you can show similarly that G1 dot A2 will be 2 pi A2 dot A2 cross A3 is equal to A1 dot A2 cross A3. This is 0 because A2 is along the plane, A2 is perpendicular to A2 cross A3. So, this dot product has to be 0, and similarly G1 dot A2 is equal to 0, G1 dot A3 is equal to 0. So, Gi dot Aj, which is equal to 2 pi delta Ij, can be generated using the Gi's which actually satisfy this condition is given as 2 pi A2 cross A3 divided by A1 dot A2 cross A3, G2 which is 2 pi A3 cross A1 divided by A2 dot A3 cross A1, and G3 is 2 pi A1 cross A2 divided by A3 dot A1 cross A2. One can show that if you use G1, G2, G3 of this form, they will satisfy this condition. So, from A1, A2, A3, you can generate another set of vectors G1, G2, G3, which can be expressed in terms of A1, A2, A3, but they satisfy a very fundamental condition that Gi dot Aj is equal to 2 pi delta Ij. This is a very necessary condition. Now, a few words about this denominator. A1 dot A2 cross A3 is nothing else but the volume of the cell which is defined by these vectors A1, A2, A3, and A1 dot A2 cross A3 is equal to A2 dot A1 cross A3, which is also equal to A3 dot A1 cross A2. So, at the denominator, all of this is nothing else but the volume of the real space. This is the volume of the cell in real space, which is defined by your fundamental translation vectors A1, A2 and A3. The points which are generated, so I have said that you have a set of real space points which are generated with A1, A2 and A3, and you have another, you can generate another set of points which are G1, G2 and G3. The points which are generated using this are called the points of the reciprocal lattice. This is a very important concept, that corresponding to every crystal you have a real space lattice, and corresponding to every crystal you can also do another geometric construction where you can define the reciprocal space lattice G1, G2 and G3. So, corresponding to every real space point which is defined by linear combinations of A1, A2 and A3, you can generate another set of geometrical points. Both are geometrical constructions. For a crystal, you can generate a real space lattice using linear combinations of A1, A2, A3. There is another set of points which you can generate not in the real space. Okay. There is another set of points which you can generate with these vectors G1, G2 and G3. Those are the points which are generated, which are called as the points belonging to a reciprocal lattice, and they are in a space called as the reciprocal space. Simply put, let us take a cubic lattice with lattice constants as A, and these are your x, y and z. For this cell you can define A1 as Ax cap, A2 as Ay cap, A3 as Az cap. A1 dot A2 cross A3 will be the volume A cube. A2 cross A3 will be equal to A square y cap cross z cap, which is x cap. So, G1, which is 2 pi A2 cross A3 divided by A1 dot A2 cross A3 will be equal to 2 pi by A x cap. So, G1 is along the A1 direction. If you recall, A1 is A x cap. So, G1 is along the A1 direction, but whereas in the real space A1 is A, the reciprocal space vector has units of 1 over length. The real space has units of length, the reciprocal space has units of 1 over length. Similarly, G2 will be 2 pi by A y cap and G3 will be 2 pi by A z cap. So, corresponding to a crystal which is cubic, you can in real space generate cubic set of points these are your cubic lattice points in real space whose spacings are A, and you can define your lattice vectors A1, A2, A3, and using those lattice vectors A1, A2, A3 you can generate the full space of lattice points. But you can also generate using G1, G2, G3, which is also a square lattice, another set of points. Let me draw it in blue. So, corresponding to this crystal with real space, you can also generate equivalently another set of points which is governed by G1, G2, G3, as given here, which also happens to be a square lattice, but now the lattice constants here are 2 pi by a. Rather than units of length, they are units of inverse of length. So, this is in real space, this is in reciprocal space. Reciprocal because they are inverse of length. Okay. So, corresponding to every real lattice, you can generate another lattice using your reciprocal lattice vectors. These vectors are called as reciprocal lattice vectors. And your here you have a translation vector R, which is written as linear combination of n1 a1 plus n2 a2 plus n3 a3. Here your vector, which is your translation vector in reciprocal space, is h times g1 plus k times g2 plus l times g3. So, you have for every lattice you can do two types of geometrical constructions. One is the real space, which you are familiar with a1, a2, a3, linear combinations of a1, a2, a3, and corresponding to the same lattice in reciprocal space you can generate another set of points with these vectors g1, g2, g3, which you can calculate explicitly using the condition that gi dot aj is equal to 2 pi into delta ij. This condition gave us these expressions which help us to calculate your reciprocal lattice points, and the reciprocal lattice is inverse of length, and as you see for the cubic lattice it is 2 pi by a. A is the lattice constant of your cubic lattice. So, this is a very important concept of a reciprocal lattice. Corresponding to every real lattice you have also a reciprocal lattice, and it is very useful for understanding the properties of the crystal. By using the reciprocal lattice for a given lattice, you can understand various properties like diffraction of waves through the crystal, which we will do next in our coming lecture.